I was before talking about controls and stuff. Well, another way of improving controls and is to also explore your outside environment so you can learn a little more or adapt to it. So you can figure out if you push the button A, how will it respond back in B? So in the future you can respond better and predict how your environment will interact with you. Now, how would you do that? Well, I want to talk about a couple methods. One way is to introduce a little randomness in your system. Not too much, not too little. Too much randomness and the noise is too high. There's too much just confuzzing and everything is just happening randomly, and you're never going to reach an ideal state with randomness, usually because random stuff happens, so randomly you deviate. Too little randomness and you don't explore new environments and stuff and try new things out. Another reason I had randomness is if you're trying new things out, if you're doing it randomly, you're least likely to be biased. You're more likely to explore just the most of types of possibilities. But another thing you could do, combining with all derivatives and stuff, is that the individual sensor could modify its frequency using derivatives and stuff, like I said before, rate of change, but they could use something I think called the Costa array. Now, the Costa array actually came from a problem with sonar, but you can apply to that thing. And this is sonar, if you're not familiar, works, and also radar, is you bounce a beam of, in radar's case, radio waves, and in sonar's case, sound waves in water, and you wait for them to come back, and you see how how long the beam it took to come back. You see if it's shifted in frequency or direction, or is it less loud or noisy, and that gives you information about what's going on. Now, if you really want, now the problem is you can send out one beam and wait for it to come back. That takes a long time, especially if it's slow like sound waves. Light waves do not take that long, but slower waves like sound waves, yeah, that can take a while. And sound waves, even more so than light waves, can interfere with each other and mess up your signal. Now, if I send out two, how do I not know that they did not interfere with each other or something? And if they did interfere with each other, cancel each other out, make one strong or less one, all direction. How do I separate out the two effects of two different beams? What if I'm moving and maybe the reason why they come to me at the same time was because as I moved, I got closer to what it was bouncing off of. So the order is messed up or something like that. Well, the worst thing in this case to figure out what the environment is in sonar and stuff is if your beams of energy are regular, because then it's hard to distinguish one from another one. If I send red and blue light, it's a lot easier to distinguish than red and red light. But the more regular and repetitive, the more likely they can interfere and build each other up or destructively and hard to separate out. So how do I make the least kind of like pattern-free, even though it's not the best word, not exactly, because it is a pattern, but at least like regular beam? Well, that's something called a Costa array. And the Costa array, there's many different ways of doing it. And this is Wikipedia. I know it's Wikipedia, but there's many, many different ways of doing it. And the easiest way, though, one of the easiest ways is by the Costas-Wells method, and they might do a very fancy way of doing it, but you take a prime number, you put it to different powers, each time you take the mod of it to another prime number. So in this example, 3 to the first power is 3, mod 5, you have 3 left over. 3 to the squared, you get 9 for the next number, mod 4. Mod 5, you get 4 left over, and so on and so on. And each of that is when you send out your pulse. Now, you can, if you have a very long sequence, it will actually start repeating it. But this is the least repeating for a given sequence length. you use that. Now, if we use this in a self-adjusting network, it can actually start to deduce the best what is happening in the environment and how environment interacts by separating out each distinct variable. Put in a bunch of controls in that each do a little change and each have them do this little thing, you will still end up with the same overall big control, almost at the same rapidly, but now it can better respond to the environment. So you don't even lose the amount of controllability, really. Yes, you lose the amount of controllability if you have a limited amount of resources, though, in case where the environment is not that important. And there is a limit to how long range of interactions it can see. This is to make it see as long range as possible. So it's not a perfect technique by far. This is one of the easy costless functions, but there's many other costless functions. There's actually infinite versions. There's actually infinite ways, and the higher order you get, the longer your signal is, the higher you can do it. So if you're looking at time spans of 10 seconds with shorter pulses and shorter corrections, you can do a much longer cluster array than a shorter one. But a shorter one would let you control stuff faster. So you have that back and forth. And the longer in the cluster arrays might not be good themselves because they do introduce some noise and fuzziness. So it would only be in a system with a lot of controls that this would be a useful idea, and each controls a little bit. Well, thank you very much for listening. Please like and subscribe. It really helps the channel out. I'm trying to reach 1,000 subscribers in a year and 4,000 watch hours, which is really hard, but with your help, I think I can do it. Also, if you have any ideas for future videos, comments, questions, or anything, please leave them in the comment section below. It really helps the channel out. Thank you very much. Goodbye.